We are getting ready to go on another journey together in organic chemistry. I know you're excited. I know you can't wait. But we're going to focus on a different type of family of compounds this time, right? We don't want to leave anyone out. And the group of compounds that we're going to focus on is something called alkene, not alkane. Now, alkanes is what we talked about last time, right? We spent hours talking about alkane structure, alkane 3D shape, alkane nomenclature. And we're going to do the same thing with alkanes. We're going to treat them fairly, but I need you to understand that alkane is not the same as an alkene. Yeah, I know. We kind of mentioned this hopefully in general chemistry, and what we talked about in general chemistry is that one letter could make a world of difference, and here is our letter that makes a world of difference. It's an A and an E. Folks, that's the only difference between this classification group as far as the naming goes. A and E with the name of the group of compounds. So this is a common problem that people have. They kind of skip over this in lecture, and they just say, today we're going to talk about alkenes, and they just go. Well, I need you to understand that alkene is a different family of organics, and we're going to talk about what type of family that's going to be today. There's a very minor difference as far as the structure goes, all right? So first off, alkanes are not alkenes. And we're going to go back and we're going to review a little bit about alkanes first, just to kind of pull in that previous lecture module into this one, clear up any confusion that you might have, and maybe relate this to real-world experimentation. So the very first thing that I want to talk to you about is the gas pump. Well, chances are that today or yesterday or sometime this week, you have made a pit stop at the gas station. And on the gas station pumps, what are you going to see? You're going to see this word octane, don't you? You ever thought about that? Minimum octane rating? Folks, you're in organic chemistry now. You should realize what octane means at this point. Octa means how many carbons. I hope that you're going to tell me 8. And if you did, you're correct. So here's the problem, though. A lot of people think octane is 1, 2, 3, 4, 5, 6, 7, and 8. And they say the octane rating is based on an 8-carbon chain. Wrong. It's kind of a misnomer here. All right. The good news is that it does involve 8 carbons, but they're not in a straight chain. The octane rating is really based off of a compound called 2,2,4-trimethyl pentane, not octane. So where does the octane number come from? Well, let's see. Well, pentane is my family name. 1, 2, 3, 4, and 5. And then at carbon number 2, I have a methyl group. All right, so there we go. And then at carbon number 2, I have another methyl group because it's listed twice. There we go. And then at carbon number 4, I have another methyl group. So there we go. So there's the skeletal structure for 2,2,4-trimethylpentane. All right, well, if I didn't want the skeletal structure, I could include the carbons and the hydrogens if that's what I want to do. So this carbon is a CH3, and then we have that attached to a carbon that is a carbon at least, but that one has a CH3 group pointed up and a CH3 group pointed up. We'll do the same thing there, not a big deal. And then that goes on to another CH2 compound or piece of the molecule. And then that one goes to another carbon that has one hydrogen, and that also has a methyl group, and that also has a methyl group. So there you go. There is the more what I would call Kekulé structure of 2,2,4-trimethylpentane. Now, some people don't like to write these side by side. If you do, I'm not going to count it wrong. Okay, but if you don't like that and you want this to have a little bit more room, then we'll just erase that CH3 that we've pointed up, and then we'll just point it down. That's not a problem, all right? It means the same thing. How am I going to count this wrong? I can't. And if you have an instructor that does, you really need to have a serious sit-down conversation with them. Okay, so there we go. Something else that we could maybe do here, this carbon in the front end, this one, it's attached to 3 methyl groups, isn't it? Look at that. One on the top, one to the side, one pointed toward the bottom. So I could actually rewrite this as something that looks like that. That's what that represents. All right, and then we go to CH2, and then we go to a CH group. But look, this has a CH3 group pointed up and one pointed over to the right-hand side. So these are 2 groups, and I can save me some time if I just do a CH3 like this and write a 2 after it. So if you see these parentheses, that is what they mean. All right, so here's the long haul of the story. I told you we're looking at octane rating, and octane rating does not involve N-octane. It involves 2,2,4-trimethylpentane. Well, 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, and 8. So this is where octane comes from. Octane is not in reference to a N-octane group. It is an octane isomer. And that isomer is a 2,2,4-trimethylpentane molecule. This gives you 100, all right? If the gasoline was purely 2,2,4-trimethylpentane, this is going to be an octane rating of a 100. And then they can lower this down depending on your engine requirement in your vehicle by mixing other organic compounds with it. And things like heptane, well, heptane really has a octane rating of 0. Hexane has an octane rating of a 0. So you can see how they can proportion this stuff out, make a blend, and that blend is going to get sold to you in a gas station. And that's where this octane rating comes from. And that's also where this 91, 89, and 87 number comes from as well. It is just dependent on the mix of alkanes that they put into that gasoline sample that they sell you. And some of our engines, it needs to be a little bit cleaner than some of the others. So most of the time, high dollar vehicles, BMWs, Mercedes, and so forth, they need the higher grade gasoline in order for your engine not to knock and feel like it's going to fall apart. All right, so that's real life organic, and you've done it probably every week throughout your entire life so far, and you'll continue to do it. Now, once we talk about gasoline, this is going to lead us into this image, and this image is really going to focus on crude oil. Now, I know that a lot of people, especially environmentalists, will have problems with crude oil. But folks, I'm going to give you a bitter, jagged little pill in the terms of Alanis Morissette. All right? And your jagged little pill basically means you got to have it. You have to have crude. So you can go out on the streets, you can protest, you can say that you are green through and through from head to toe. But I guarantee you that you have gotten to a vehicle and you've put gasoline into your car to get somewhere wherever you're going. And maybe you put gasoline in your vehicle to go to that environmental protest that you've attended. And I'm not knocking you if you do go to those protests. But what I'm saying is that you can't have it both ways. You can't say we don't want crude oil and then turn around and put the remnants of crude oil into your car to go to wherever that you're going to. Get me? Get my drift? All right, so you see where I'm going with this argument. Also, at the same time, crude oil, if you are protesting the extraction and use of crude oil, then we need to go to your house and we need to chop off your electric. Okay? Your electric in your home, the electricity that you get, is strongly related to crude oil. All right, now what is this idea of crude? And folks, let me tell you something. I'm going to go back to this here, And let's say that you are environmentally conscious and you have purchased one of those vehicles, and those vehicles are chargeable, right? Oh, it makes you feel so good when you drive it. All right, and maybe it does, and that's great for you. So if you want to go out and buy something like a Tesla, go do it. But here's the problem. You take your Tesla home and you plug it up. Where do you think that electric's coming from? That electric is coming in a roundabout way from crude oil. So you're still using it. You're still depending on it. It's just in an indirect way that you are depending on it. All right? So keep in mind, crude oil is not going to go away. You can protest it. You can say that it's environmentally hazardous, and sometimes it is, right? Especially when you see pictures like this. But there is no good alternative at this point in time. I can put up as many solar panels as I want. I can put up as many wind turbines that I want, but it's not going to give me the high energy that crude oil is going to give me in the long run. And that's the problem, folks. That is why solar and wind, one of the reasons that solar and wind and alternative energy has not really made its way into mainstream yet. It's not perfected. And the end result is not as good as something like crude oil, or even more so, nuclear. All right, so here is an image of what you're seeing on the screen, and this image is called a fractionation column, okay? And we're going to maybe do fractionation in the lab this particular semester and in this class. So what this image is basically showing you is that I'm getting crude oil that's down here in the very bottom. And crude is just a mix of different hydrocarbons that we will use in a lab. And the ingredients to many of the things that we use every day, like gasoline for my car, the tar and the asphalt to put onto the roads, okay? All of the organics that's used to make plastics, and those plastics are turned around and made water bottles out of, or the protective casings on your phones. All of that is related to crude oil, every bit of it. The diesel engine that you put in diesel, right, vehicles. The jet fuel that you need in order to fly from one coast to the next. All of the lubricating oils that we use in industry or maybe at home. I don't know. All of those materials are coming from crude oil. And this is one of the reasons that we really can't ignore it. All right, so this crude is heated, and as the crude is heated, all of the liquid volatiles will begin to turn into a vapor, and that vapor will slowly begin to escape. And sometimes this vapor will stop, and it doesn't really get heated anymore. And then we can soften all of that material off and collect it into what we call a fraction. And this is what we call fractionation distillation. As we continue to heat, those vapors could go up and over, up and over, up and over, and the really, really light boiling points will tend to go toward the top of these fractionation columns, all right? And if they're really, really low boiling points that go to the top of the fractionating columns, this area is typically our gasoline blend. But as you can see, as we go up those fractionation columns, we have everything from gasoline to kerosene and jet fuel, all of the lubricants that we use for many different purposes in life, fuels for ships, diesel fuels, lighter fuels, and so forth. And these compounds are also turned around and used in a laboratory environment to make everything as far as plastics go, your things that hold the cosmetics, all of those cases, any kind of plastic tub, all of our pharmaceuticals can be synthesized from different fractions within the crude oil category. Folks, crude oil has tons of stuff that we need on a daily basis, and this is just one example. So, if you ever go to Texas or Louisiana or another area that is known for their oil refineries, this is what an image that you're going to see. And now you kind of know what the purpose of some of these really tall towers are going to be. I'm not saying that every one of them is that way, but anytime that you see these really tall looking towers, it is a very good sign that this is what's going on the inside. So that is a fractionating column for the oil refineries, so that way they can turn around and change it into gasoline and sell it to you at the gas pump, so that way you can come to this class, or you can power the computer that you're using right now, or that you can power your phone that you carry with you throughout the entire day. You are dependent upon that oil if that's what you do. All right. Another term with alkanes. Here you see a picture of a dead fish, all right, and some lemon on it. And very often, if you're a seafood eater, you will maybe become accustomed to knowing that if you squeeze lemon juice onto some fish, it might make the fishy odor go away, and it might actually make the fish taste a little bit better. So this fishy odor is typically related to the group of compounds that are called amines. And we learned about amines in the last module, didn't we? Amines were NH2 groups. So wherever we saw an NH2, we called this an amine, and we began to name them and draw structures of them. And amines are notorious to be stinky. All right. If I really wanted to make a student's life miserable, what I could do, right? What I could do is go to our stock room and get an amine, a very small amine, and put it on a rag and just wipe it all on the inside of their lab bench, all in their lab drawers, right? If I really wanted to make their life miserable, I could take an amine and I could take a rag and get some amine on it and smear it all over their assignments, like lab reports and tests that they hand to me, and then give it back. And that odor is going to smell like dead fish by the time they get it back. Could you imagine? Could you imagine? I can. All right. So, for example, what they say here is fermented shark is a traditional dish, and it smells exactly like triethylamine. So this is the compound triethylamine that is smelling like fermented shark. I don't think I want to smell fermented shark. I don't want to do that, right? But we can draw the structure of it. We're in organic, right? We're learning to be organic chemists with this class. So triethylamine. All right, so amine is a nitrogen group, and triethyl means I've got 1, 2, and then maybe 1, 2, and then maybe 1, 2. I just did the skeletal structure there. So here's an amine group. This nitrogen has 3 bonds with it now. It doesn't need any hydrogens. And if I wanted to put those free dots there, I could, but typically in skeletal structures, they're not unless you're going to do something with them. All right, so there is the smell of fermented shark. All right, but you're also going to see cadaverine come from this family of compounds as well. That's the smell of a dead body. Decomposition, all of that is amine based. All right. And then in this diagram, they're also telling you about citric acid in lemon. All right. Well, amines, we know, have very high pKa's, don't we? We know they're in their 40s. And if we take something like a lemon or something acidic, and that in particular is citric acid, that citric acid and this base react together. And when this does that, look down here at the very bottom. Here is triethylamine drawn out, and then here is your citric acid molecule. There's a lot there, but I want you to focus on these carboxylic acid groups. Do you see that? C double bond OOH, C double bond OOH, C double bond OOH. These are carboxylic acid groups, and there's actually 3 of them on this molecule. And we know what pKa's that carboxylic acids bring, right? And we know the reaction between acids and bases at this point. We learned that in the last module. So this is an acid, this is a base. And probably what goes on is that this base will be attracted to a hydrogen on that acid, and it rips it off. And I can draw the curvy arrow mechanism here. And then I end up with this kind of compound, and this is a protonated amine group, and this is odorless. So I don't smell the dead fishy smell anymore. If I squeeze at something like lemon juice, maybe lime juice, maybe some orange, maybe not as potent, but it's still there. It's still citric. It's still an acid. And then we'll end up with a citric acid molecule that has a hydrogen that's missing. Now, what they did is that they focused on this hydrogen here. And that's really what I should have drawn here, because there is a little bit of difference between the acidities of these hydrogens that's on the molecule. You don't know that yet, and that's why I just drew it to the next neighboring one. And if that's what you did on a test, of course I would count it correct. All right, so triethylamine is a base. It smells bad. It's stinky. And then citric acid is an acid, and this has some hydrogen that it can give off, definition of the acid, and that amine can pull that hydrogen off, become protonated, and now all of a sudden that smell goes away. Here are a couple of more amines. You can have more than one amine group on a structure. No one says that you can't. So I can have one NH2 group, two NH2 groups, three NH2 groups, and so forth. I want you to take a look at how they name them, though. Here we need to find the longest carbon chain, right? So it looks like there's a carbon, there's a carbon, there's a carbon, and there's a carbon. So that's where butane comes in. And then on carbon number 1 and on carbon number 4, there are two NH2 groups. So 1,4 is there for that reason. Di, because there's two of them, and the word amine, because there's two amine groups. So this is something maybe we didn't elaborate on in the last lecture module, but it is something that we can build upon, and that's part of organic chemistry. All right. In the next one, we've got 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. That's where the word pentane comes from. And there's two amine groups. So this could be pentanamine, but it's not, because I need to label both NH2s. So on carbon number 1 and on carbon number 5, I have two NH2 groups, right? One on each. So di and the word amine. These are, of course, the common names that go along with the IUPAC name. And as you can tell, just by looking at the names, if something smells putrid, well, it's putrescine that's coming from it. All right, and now you know the structure of it. It's really a 1,4-butane diamine. The smell of a dead body, a cadaver, well, that's 1,5-pentane diamine, and now you know the structure of that. Something else that we talked about in the last lecture module was bonding, right? And we talked about dispersion forces. We talked about dipole-dipoles. We talked about ion dipoles. And we also talked about hydrogen bonding. And what you're seeing here in this diagram is the image of a DNA molecule. All right? So the DNA molecule has your genetic code, and it's very stable, right? This DNA molecule, it will last for as long as you live. If you spread your DNA, let's say on a crime scene, it will stay there until a forensics analyst will be able to pick it up and identify who you are. If you work in a restaurant and you are delivering food to your table, well, you probably at some point in time have put your DNA, whether you realize it or not, onto the food that you are serving to the people and the customers that are in your business. And if you're eating that food, you need to understand that you're eating the DNA of whatever you're eating. Maybe it's a pig, maybe it's a cow, maybe it's a chicken, but you're also eating the DNA of probably the cook that made it and the server that delivered it to you. So the next time you go in and sit down at a restaurant, think about all those wonderful thoughts and ideas and relate that to the world of chemistry and biochemistry. So the hydrogen bonds that are in DNA, you're seeing those here with the dotted lines. This is what really holds the DNA strands together. DNA is a double-stranded molecule, And this double-stranded molecule means I've got a strand that's here and I've got a strand that's here. And we need glue that holds those strands together. They are what we call complementary to each other. And complementary basically means it's kind of like almost like a mirror image in a way. It reads backwards. And I can take one strand and use that one strand to replicate the second strand, and I get back the original DNA molecule that I started with. All right. All of this glue that holds these strands together to make this a very stable molecule, all of those are hydrogen bonds. So basically, hydrogen bonds, if you remember, are hydrogens that are on an N, O, or F, and it's attracted to another N, O, or F on another molecule. This also gives DNA its shape. So the hydrogen bonding that begins to take place, this is just one way to represent the DNA strands. It makes it a little bit easier to look at and study, but at no point in time are they really parallel like this. They do not go straight up and down on a sheet of paper. They do have shape, they do have 3D structures that are associated with them, and that's where the DNA helix comes from. All right, so the DNA helix is a curvature in the DNA strand. And this curvature or coil, think of a slinky, the way that this is formed, it's held together and stabilized by hydrogen bonds. So not only does it keep the two strands together, but those hydrogen bonds will also provide the DNA its typical helix that we talk about in classes like biochemistry and biology and so forth. Something else that we want to talk about organic are, of course, the pharmaceutical industry. The pharmaceutical industry makes pills or makes the ingredients to make the pills, okay? And in a pharmaceutical company, you are often popping out left and right, one organic after the next. Now, I know, how does this really get involved with what we talked about in the last module? Well, the last module talked about forces. It talked about interactions of molecules, right? And the way that these pills work is that they are embedded with organic compounds. And whatever organic compound that is, that's the active pharmaceutical ingredient. We call that API, active pharmaceutical ingredient. So when I take these APIs and I give them to you and you swallow them and they go into your belly, and then you drink a glass of water and you wait 4 hours, or it might be immediate. It could be a slow release. It could be immediate release. I don't know what kind of pill that you're taking or what your doctor has prescribed you. But whatever you do, you are relying on this API to go to the site that is bothering you and to take care of whatever ailment that is. And this drug all relies on interactions of molecules. It's interactions of the API, and it's also interactions of what we call the receptor sites. And the receptor sites are areas that are also organic in nature. They could be protein, they could be amino acids, it could be a number of different things on the surface of a cell or at the site of location that you want targeted, but that is an organic structure. And these APIs are also organic structures. So this API goes to this site that we call the receptor site, and they begin to have an interaction between the two. And this is what makes that ailment go away, or it's what makes that ailment a little bit better for you. Maybe it can't disappear, but it gets better over a course of time. All right. Here's another way that we can relate what we discussed back in the last lecture module. What you're seeing here is an image that they typically give you in a class like biology, and they say, listen, here is what we call a surface of maybe a cell, and then here is another surface on the opposite side, and all of these are what we call polar heads. All right, so this is going to be on the outside of the cell, and this is going to be on the inside of the cell, and there's a barrier here, and that barrier all has non-polar tails on them. That's what we call this. So now, from that last lecture module, we can relate this term non-polar and polar to the world of something like biology. And biology really is chemistry-based, believe it or not. I mean, that's how it all is driven. All of this is possible because of chemistry. We just look at the smaller things, and they look at the larger picture. That's just a different point of view that biologists and chemists have in real life, okay? So here we have polar heads, and these polar heads, of course, are not going to let anything organically come in through that barrier. Once or something organic-y comes into play, bink, it goes right off. All right, it doesn't want to associate with it at all. So this helps create a division line, a border, if you want to talk about it that way. It's a border between the exterior and the interior of the cell. On the inside, these are all nonpolars. So we can see nonpolar structures on the inside of that lipid bilayer. And this is what we call cholesterol. Cholesterol is going to be something very common that we see squeezed into that nonpolar area of that bilayer. So it's just a moment where chemistry and biology come into play. If you want to take a look closer at all of these individual molecules that make this bilayer up, they are typically due to phospholipids, and here is an example of a phospholipid. So these are the tails that are mainly nonpolar, where cholesterol and other organic-y types of materials like to hang out. And then on the surface, or the head of that compound, we have something that's a little bit more polar. And you can see where the polarity comes from. Look at these oxygens. They carry free dots, don't they? And then here is an oxygen. They also carry free dots. So I'm seeing a lot of polarity that's associated here in this molecule structure. And then if it's a phospholipid, I'm seeing even more so as far as polarity goes, with a full-blown negative and a full-blown positive that's right there. Okay. Another thing that we can relate to what we talked about last module is equatorial and axial bonds. So here's an image down here at the very bottom of carbohydrates. And carbohydrates love to be classified as sugars, and if you eat a lot of bread, you might see yourself gain weight a little bit, and that's because these carbohydrates are broken down into glucose, and that glucose is stored as energy, and that glucose can actually also be stored around your hips and your thighs and everything else that you don't want. So in the long run, your body will go to those savings accounts that we call fat, and that will be pulled out. And of course, that's mixed with other things as well. But glucose is going to be one of those energy reserves that it can store, and that glucose can be broken down into energy that your body needs. All right, well, here's the structure of glucose that you see on the screen. And what you see is that these are individual glucose units, right? Here is one unit, here is a second unit, and there is a third unit. Notice what's on the glucoses. You see a lot of OHs, you see a lot of polarity that's associated with them. Glucose is a polar compound. And then, in addition to that, look at how they've drawn the structure. This is a six-membered ring. Well, it's got oxygen in one of the spots, not carbon fully, so it's not a cyclohexane, but it's very similar. And look how they've drawn it. They've drawn it almost like a chair, haven't they? This is a chair structure of a glucose unit. On these carbons, you have equatorial and axial bonds, and we've talked about those in the last lecture module. So equatorial and axial bonds, if you take a look at the way that this is drawn, this is straight down, so therefore this is an axial bond. And this one goes kind of out and slightly down. So this is an equatorial bond. And if you get an axial and an equatorial bond, this is going to be a structure that we call amylose, and that amylose can be stored and broken down to free up individual glucose units. However, if we switch the equatorial and axial bonds and we do something like this, all of a sudden, we're not talking about amylose anymore. We are now talking about cellulose. Okay, which one of these do you want to eat? Do you want to eat this nice little bagel and maybe make a sandwich with this what looks like wheat bread? Or do you want to eat this cotton? Just the difference of axial and equatorial bonds will cause the major difference that you're seeing here. And now you know why axial and equatorial are so important. Okay, it's not something that I'm introducing to drive yourself crazy with. But axial and equatorials are very important in terms of organic and in terms of chemical structure, because just the flip of one of the axial bonds, and now we're looking at equatorial and equatorial. It's the same glucose units. There's nothing different with the glucose. There's no difference at all. But with the axial bond getting flipped to become an equatorial bond, we change the structure of the major organic. And when we do that, we go to something that we call amylose to something that we call cellulose. All right. So there's a quick review, maybe not a true review, but a review of why we talk about the things that we talk about in organic chemistry and how it relates to your daily life. Okay. So in the next video, we will then start talking about alkenes. We need to figure out how alkenes are different than this world. Right? This world was mainly alkanes. It was also a little bit of polarity, non-polarity. It was axial, equatorial bonds, a little bit about 3D structure. So now we need to see how alkenes will change the game. And we need to learn a couple of new rules in doing so.